And so even on the syllabus, you'll notice that we were doing statistical thermodynamics, the first couple of weeks of school. We didn't actually get to this point, so I want to go back a little bit and finish out this USHAG. It's internal energy, entropy, enthalpy, Helmholtz energy, Gibbs energy, and then the equilibrium constant, because that's one of the thermodynamic values that you can calculate using the Gibbs free energy line on the Gaussian output file, is you can calculate equilibrium constants. Okay, and so I wanted to cover this, sort of the connection of Gibbs energy to the equilibrium constant, just to make sure that you are on the same page with me in terms of your thinking about how those are related. Okay, so we were talking about statistical thermodynamics. The statistical part is that Boltzmann distribution, sort of the molecules are colliding with each other. Argon at 1 atmosphere is hitting other argon atoms in a gas phase 10 to the 13 times per second. Just get your mind around that. Yeah. 1 billion times a second would be really like an incredible vacuum. 1 atmosphere pressure, they're hitting each other 10 to the 13 times per second. That's amazing. And that's in a gas. So you think about a solid or something, I mean, they're right next to each other, jostling. So that they're going to come to equilibrium very quickly, meaning they're going to have a full distribution of velocities, all of these different rotational levels. They are going to come to equilibrium very quickly because they're colliding and interacting so often. Put a hot molecule in there, it's going to get hit so many times that it's going to distribute its energy. Let's say you had a 1 in a million chance of a 3-body collision. Well, if it's hitting other molecules 10 to the 13 times, there's going to be a lot of 3-body collisions. So you may say, well, this is a 3-body collision. That's not going to happen. Yes, it will. Very few, but still quite a lot of 4-body collisions are going to happen. And in fact, you're going to have a molecule that's hitting the wall right when another molecule hits it, and drive some of that energy of that one molecule into the wall, and you're going to have energy loss. That's why it's so hard to do atmospheric modeling, because there aren't any walls in space. And you can hardly do a reaction in a chamber where the walls don't have an effect. So the statistical part is huge. Chamber wall effects are the thing that make atmospheric chemistry so difficult, because you just can't find a way to set up that experiment where it doesn't interact with the box. Okay. And then the thermodynamic part are all of these thermodynamic entities. What's interesting is all of these thermodynamic entities were developed before quantum mechanics. And so they really were resistant to quantum mechanics being true, if you will, or confirming what they knew about nature, until Boltzmann and Planck and them sort of applied this to thermodynamics. This was the real thing that said, okay, thermodynamics, quantum mechanics must be underneath all of science, because we're getting the bulk properties from a quantum mechanical model. And that's what you're actually doing in Gaussian. You're starting with the quantum mechanical model and you're getting thermodynamic properties. So if you notice, the project idea is to model a bulk thermodynamic effect using an atomistic model. The Gaussian part, you're building the atoms into that model, and that's the atomistic approach to a thermodynamic question. So the statistical entropy, we can think of entropy as, I'm sure you've heard the definition of entropy as a measurement of disorder, but it's really also a count of the options a molecule has. So the density of states, I noticed somebody put that in our Quizlet study set. That's good. Density of states, it's just how many states do you have in a joule of energy. And so it's related to heat capacity. It's related to how you can store energy in a molecule. It's related to entropy. And so this statistical entropy is related to that partition function. And we noticed with our 2-level system, as we raised the temperature, we had a higher probability of excitation. So the Q goes from a minimum of 1 at 0 Kelvin. All of the partition functions are going to collapse down to 1. You have 1 energy level populated. If you start to add temperature, you start to get more statistical options. Your entropy is going to increase with temperature, because the population of the energy levels increases with temperature. And so this is Boltzmann. He's like one of my heroes. So had a sad end. But how cool is it on your tombstone to have an equation, you know? So he's got up there at the top, S equals K log W. W is that weighting factor of all the different permutations of a system. It's related to the partition function. So here's the simple calculation we did, similar to what we did in class, a 3-level system at 300 Kelvin. So what's the partition function? You could just take those different energies, or divide by kT. We want everything in kilojoules per mole, so instead of using K, we're going to use the gas constant, which is K times Avogadro's number. So we use 0.00831 kilojoules per mole Kelvin. Then Kelvins cancel with the temperature, and the joules per mole cancel with the energy levels, and we end up with our partition function. So Q in this case will be 1.5. I chose the numbers nicely so that they would cancel out. So then the average internal energy is the probability of being in each one of those energy levels times the energy of those energy levels. And so this is just a short, quick way to write that probabilities. It's the Boltzmann factor for that level divided by the partition function. So each probability is calculated this way, and then these are the energy levels. And so then we end up with the internal energy of 1.1 kilojoules per mole. Notice we made this point earlier, that's sort of the average energy or expectation value for the energy. So if we pulled molecules out of the box, some would have 0 energy, some would have 2.5 kilojoules, and some would have 5 kilojoules. But if we averaged everything, this would be the average energy of 1.1 kilojoules per mole. And that's up here somewhere. It's like right there. Notice the average energy almost never matches an energy level. In a small system like this, a 3-level system, the average energy is going to be somewhere in between those energy levels. But if you were to pull individual molecules out, they would have those discrete quantized energies. Say again? Okay. And so then calculating the molar entropy, it really goes in order of U-shag. So you need U to calculate S. And so you put in the U value using R instead of K, and the partition function and the temperature. And so we get S. S's are pretty small compared to the energy values, because in most cases they're multiplied by temperature. Yeah?
Units should be kilojoules per mole. Okay.
Yeah, that's right. There's a K in there. Let me go ahead and make that change. Probably a copy paste here. Excellent, thanks. Okay, and so then the enthalpy, you need the internal energy also to calculate the enthalpy. So you have U plus RT. And so there's our enthalpy, 3.6 kilojoules per mole. And then the Helmholtz energy, which would be this, your thinking is probably trained to think in terms of Gibbs free energy for determining if something's spontaneous or not. And that's for a constant pressure. So you might want to write that down. The Gibbs free energy is for spontaneity with constant pressure systems. Gibbs free energy determines spontaneity for constant pressure systems. The Helmholtz free energy is spontaneity in constant volume systems. If you have Gibbs energy, remember that it's G equals H minus TS. This is U minus TS. So it's the same equation, but it's swapping out U for H. So this is the internal energy subtracting the entropy term. And so this happens to be a negative 1.0 kilojoules per mole. And then the Gibbs free energy is going to be H minus TS which is using enthalpy 3.6 kilojoules per mole, and so we end up with 1.5 kilojoules per mole. So this is just how you go through and calculate all those thermodynamic properties for a three-level system. Pretty simple setup. Gaussian is doing something similar, okay? Only it doesn't really have a three-level system. If you've got a molecule like this azaborole, benzoxide, it's enormous. You're going to have all those vibrational modes in there. So it's not just a three-level system. It's got the vibrational modes. It's got the rotational modes. It's also got the electronic. It's not calculating the translational explicitly. It's using the equipartition for the translational piece. And so these are the summary of the results. I think really just showing this, one thing to note is that a lot of times if it's in joules or kilojoules, they will, you mess up the entropy term. Again, they have the K, yeah. But you mess up the magnitude of the entropy term. So a lot of times if you're using the gas constant, you'll see 6.9 joules per mole for the entropy term, and the others are in kilojoules per mole. Okay, and so then they that's a source of calculation error then when you use it in the Gibbs energy term, that if you don't pay attention to whether it's kilo or joule, then you've got a problem. So let me go ahead and get this. Okay. Okay, so now let's talk about the Gibbs energy a little bit. There's a lot of different ways to write these thermodynamic equations. Notice earlier Gibbs energy was H minus Ts, and here there's another form of that equation. It's the Helmholtz energy plus PV. And we could substitute that PV equals nRT. You've heard that ideal gas law. Another way to write nRT with Boltzmann's constant is just the total number of molecules times Boltzmann's constant times temperature, so nKT. So that PV to nKT is just the ideal gas law. And then A to minus KT ln capital Q, the capital Q is for an ensemble of molecules. So that's the substitution for the Helmholtz energy. And so it would take all semester to derive all of these different equations separately, but let's just follow this one progression because I think you'll like what shows up. And so this capital Q is for an ensemble of molecules. You can take those individual molecular partition functions, which is the little q, and then it's for every molecule, you have n molecules, the total partition function are those individual partition functions multiplied by each other. So if you have n molecules, you have n individual q's. But if they're indistinguishable, then you're overcounting the number of possibilities. And so you divide by the number of molecules factorial. So now we have a problem because n factorial is an issue with numbers higher than about 100. So you could look on your calculator, if you type in 5 factorial, you'll get it, but if you type in 105, it's going to give you an error because it just blows up. And so there's this thing called Stirling's approximation, which helps us get rid of this enormous number factorial. Okay, and so this we also pulled out this log. We have a log of a quotient, and so that's equal to the difference in logs. So for this step, we've split that fraction, and we have now 2 logs. So we can deal with this n factorial separately. So notice how this n factorial here has disappeared using Stirling's approximation. So this natural log of n factorial is this piece in parentheses. And so we're going to have this KT here be multiplied inside, and it's going to give us a minus NKT here. So this KT minus NKT will cancel with this plus NKT. So those are going to go away, and we're going to end up with NKT ln N and NKT ln Q. So that's what Stirling's approximation has helped us do. We got rid of the n factorial. And so now we have the difference in logs. We can go back to a fraction. So going back to a fraction, we have this minus nkt little q over n. One way to write this, number of molecules is the number of moles times Avogadro's number, and Avogadro's number times K is R. So that's where R came from, and the number of moles. Okay. So now we have nRT, natural log, and we also split the number of moles and Avogadro's number out of this to give us this. Okay. Just that's what I mean. We can do that, or we can leave it like it is. But we have this number of moles in front. It's multiplied by that natural log. That also can be moved in as an exponent. So you see this little n here. You could write it as an exponent. So this is an interesting equation. We have G equals minus RT, ln something related to the molecule raised to the number of moles of that molecule. So that's the Gibbs energy for a particular species. Now let's look at a reaction. So for a chemical reaction of A, B equals C and D at equilibrium, the delta G is the number of moles of C, so products minus reactants. The number of moles of D times the Gibbs energy of D minus the Gibbs energies of the reactants times their number of moles. And so this is what we have in terms of what we just derived. We have that Gibbs energy substituted in here times the number of moles. And so those are going to end up as exponents. And remember, the difference in logs, you could write that as a fraction. And so these two negative logs can come in as a denominator. And so we have delta G equals minus RT ln in this fraction. What's on top? The top is the products, and on bottom is the reactants. That's exactly what we see in terms of the equilibrium constant. And so we have these relationships. Delta G equals minus RT ln K. Or if you want to solve for K, it's e to the minus delta G over RT. So what we've been using all along in terms of our equilibrium constants have been concentrations or partial pressures. But those were approximations of the partition function. You know, sometimes like for ionic strength and so on, your concentrations aren't exactly right. They're not giving you the right answer for equilibrium. Why is that? It's because this assumption that they're actually representing the partition function starts to break down. But for dilute solutions, or if we define it as, say, 1 molar solutions or what have you, they'll hold. But we're really approximating the partition function when we use concentration or partial pressures. So that's a pretty cool result. So let's look at some conceptual examples. So as we've already done this response to heat, we get a higher entropy as we add heat because we have more energy levels populated. If we squeeze the system, this is one way to understand what happens to the density of states if you put pressure on something. So you can actually impact things with pressure. And that is, you're shrinking the size of the system. And so from the particle in a box analogy, if you have a smaller box, the energy levels are further apart. If you have a bigger box, the energy levels crush down. So responses to pressure can affect those energy levels. And so we can talk about this density of states changing with respect to pressure and other factors. Now let's look at equilibrium. So in this case, we've got reactants and products, and it's an endothermic reaction. It's uphill in energy. And we've got these gray bars sort of represent the population. So the ground state has the most number of molecules. So that would be the Boltzmann factor divided by the partition function for the ground state. So the probability of the ground state, probability of the first excited state, probability of the second, third, fourth. Notice when we get to this one, it's in between this one and that one. So we throw all of the energy levels into the Boltzmann distribution calculation. So think about it. The Boltzmann factor or Boltzmann distribution has no idea what's a reactant and what's a product. It only has an idea of where that energy level is. Think about that. So when it gets to this point here, let me find my pen. Okay, when it gets to this point here, the very next energy level happens to be a product energy level. And so it's slightly less probable than this energy level, but slightly more probable than this one. So it's in between those, and so its probability reflects that. Okay, and so you can come up with the Boltzmann distribution and the Boltzmann factors for all of these energy levels, regardless of whether they're products or reactants. But now if you wanted to calculate the equilibrium constant, you would sum all of these and take products over reactants. Notice how the reactant sum is a lot larger than the product sum in this particular case. And so what would you estimate K to be? Yeah, it'd be less than 1. Okay? Because the denominator is larger than the numerator. So the equilibrium would lie on the reactant side, on the left side. Look at this example. The density of states has an enormous impact on this one. We still have an endothermic reaction, but because the products have so many energy levels, statistically they're going to be favored. So we do the Boltzmann factor here. So we have this big probability of being in the ground state. Then the next probability is in a product. The next one's a product. The next one's a product, product, product. Then we get a reactant, then more products, then another reactant, then more products. And if we take all of these and sum them together and do products over reactants, we actually see that the products are favored. And so this would be an equilibrium constant that's greater than 1. So this is a statistical explanation how some spontaneous reactions can be endothermic. Most of the time these exothermic reactions are exothermic because of the entropy. It's really driving the reaction forward. It's giving off heat. So it's negative delta H and a positive entropy. So there's no way that the Gibbs energy can be positive in that case. If delta G is equal to delta H minus T delta S, and that's positive and this is negative, you see a positive change in entropy, so more disorder lowers delta G. And if you have a negative delta H, an exothermic reaction, that lowers delta G. So that's a beautiful spontaneous reaction. That's combustion. Okay, a fuel that's a kind of a big chain hydrocarbon mixed with oxygen produces a whole lot of moles of CO2 and a whole lot of moles of water. And so entropy goes up enormously if you're burning a good-sized hydrocarbon, and so that's a big delta S, and it's giving off a lot of heat, and so you have a really spontaneous reaction. Okay. But sometimes you have an endothermic reaction, so this is plus, and so you need a big enough density of states in your products to drive the reaction forward. So the one shown on the board has got a big double plus entropy and a plus enthalpy, but because this is large, that negative sign helps drive delta G to be negative.
So this is like an ice pack.
Yeah, and it's a heating pack or an ice pack. That would be an ice pack or a cooling pack. Yeah. So something in there is sucking up heat. A little tricky to do in a bag like that because you can't use the generation of gas. A lot of times the generation of gas is what drives the huge entropy change. And so you can get endothermic reactions that release a lot of gas. And the classic one is barium sulfate and I can't remember. It's two solids, okay? You put them in a beaker and you mix them together and they generate ammonia gas, and that drives the entropy. It'll fill the room with ammonia gas, so I don't ever like to do it, yeah. But it gets really cold. I mean, it'll freeze, you know. So what they typically do is they'll put it on a wet piece of wood, and they'll stir it for class. And you'll see this. You can look at this on YouTube. And then they pick up the beaker, and the wood has frozen to the bottom of the beaker. So it's a little showmanship. And so then this equilibrium example is just given to you to show, you can go through this and look at the density of states on the right. Can give you a spontaneous reaction at lower in energy and so on. So you can look at those numbers. let's go on to the thermochemistry piece though. Because this is super important for your calculations. So this is just the studying of the heat exchange and chemical reactions. These are some of the easiest calculations to do because you look them up in thermodynamic tables. So delta H of formation, right? You can look that up and you can figure out what the delta H of reaction is by finding the reactants and products and subtracting the reactants from the products. Okay. You could do the same thing with Gibbs Energy and with entropy. But in order to come up with those, you need standard values. And so we've decided as a community of science what the standard temperature and pressure are. So standard temperature for these thermodynamic tables is 298. And the pressure is 1 bar for these thermodynamic standard tables. Now that's not for the gas law. What's the standard temperature and pressure for ideal gas? They use atmospheres. So it's 1 atmosphere for STP in gases, and it's freezing water. So it's 0 C, which would be 273 Kelvin. So don't get those mixed up. For these thermodynamic tables, they use these the thermodynamic standard temperature and pressure, and they use bar instead of atmospheres. I don't know why. It drives me crazy. They're 1% different. You know, does it really make that much difference to use bar versus 1 atmosphere? Why couldn't they just leave it? You know, the standard temperature and pressure with the ideal gases is a much older standard. And so I don't know why they didn't.
It's like 1.0185.
Yeah. And then standard volume is irrelevant. So why? I just put that in for discussion. So why do they not specify all 3?
Talking about Gibbs.
It's just this. No, just these. Think of it the ideal gas law. Yeah. If we were to lock down the volume, so we've got 4 variables: temperature, pressure, volume, and what's the 4th that we don't really think about much? Number of moles, right? So if we locked down 3 of the 4, we would lock down all 4. Right? So we got to have some degrees of freedom here. So we leave volume and moles to fluctuate with each other. So volume and moles are flexible, and the temperature and pressure is all we need to lock down. So we have physical changes, vaporization, fusion, and sublimation, and this just shows that they're additive. So if you have fusion and vaporization, that's the same as sublimation in terms of energy. You can go from solid straight to gas. You can go through a liquid as an intermediate stage. But these are state functions, which means if I'm in the gas phase, it doesn't matter how I got there. I could have come straight from the solid, or I could have come from the liquid and then the solid. Okay. And so this is our definition for standard reaction enthalpy. And there's some important words that are underlined, as you can see. So pure unmixed reactants in their standard states that become pure unmixed products in their standard states. So this is really, it's really got some problems for aqueous chemistry, because the water cage stabilizing ions can have a very large enthalpic effect. And so these are to be taken with somewhat of a caveat whenever you're doing these standard enthalpies of reactions, because just mixing salt and water, you can feel that there's a temperature change, and it's not always exothermic. Sometimes it's endothermic. It just depends upon the order of the system. You're changing the entropy. Hess's law, which just means that the reactions can be added together along with their enthalpies. So you can take a reaction and you can add them together. And let me just show an example. So you have this reaction, and it may have a delta H of reaction 1, and then you have a second reaction of C plus E gives, let's just say F. Okay, so they combine to give F. And then this is delta H, reaction 2. But you can add these together and cancel like species. So C can go away, and then we have A plus B plus E gives D plus F. And so you don't even see C in the intermediate reaction. And so then this is the sum of all of those delta H of reactions. Okay. So that's Hess's law. Essentially, you can add the reactions, you can add the enthalpies. This helps us do things like this. Okay. So we want to know somehow the formula, the formation of ammonia, and we do this in intermediate steps. And so how they got this experimental data, I don't know, but they've taken the nitrogen and hydrogen here, and they've got half a mole of N2. They have to use N2 versus N atom, because you'll see here N2 is not the same as N atom. So we have half a mole of N2, which is essentially 1 atom of nitrogen, and 3/2 moles of H2, which is essentially 3 hydrogen atoms. But we need to use these species because these species are defined as 0. That doesn't exactly line up, but it should. Okay. And so that's the thermodynamic definition of what 0 is in terms of enthalpy of formation. That's a really important point. We've defined where 0 is. And so in taking those molecules apart, up here we have the energy of the 3 atoms of hydrogen and the 1 atom of nitrogen. So that took, golly, that's like 1,000,000 joules to do that per mole. So 1,000 kilojoules to do that. And then we start reacting at 1 atom at a time. So this, putting 1 hydrogen on the nitrogen gave us 300 kilojoules. Putting a second hydrogen on the nitrogen gives us almost 400 kilojoules. And then putting that third hydrogen on gave us almost 500 kilojoules. And once we put all 3 of those hydrogens on, we have NH3. And so we could have added all of these reactions together, and we would have 3 hydrogens on the left and 3 individual hydrogen atoms on the right, and the individual hydrogen atoms would have canceled because they're on the left and the right. And we would end up with ammonia. So we could see Hess's law in action here. We could see the energetics. And then we have delta H here for the reaction is the sum of all of these. The sum of this positive one and then the subtracting all these negatives. Okay. But Gaussian is different. Gaussian has a different reference point. And this is why your numbers are all huge and negative. Okay? So Gaussian is using as its reference point, look where 0 is up at the top. And look what is defined as 0. So nitrogen nucleus, which is 7 plus, and the 3 hydrogen nuclei, H pluses, and 10 electrons, all separated to infinity. Now this is a nice reference point because no matter what you form chemically, it's going to be downhill from pulling 7 electrons off of a nitrogen nucleus. That's way up there. So even if you form nitrogen 6 plus, okay, it's going to be downhill from this. So every energy you calculate using ab initio or DFT should give you a negative energy. Yeah. The semi-empirical folks, what you're calculating, you need to check that to see what the semi-empirical reference point is. So you need to go into the help file and figure out what the semi-empirical reference point is, because I don't know it myself. I've done mostly DFT calculations. So if your project's using semi-empirical, that's one of the problems you're going to have to overcome. And I want to see that in your report prominently displayed. This is the reference point for my semi-empirical calculation so that I can learn something from your projects. Yes. And if you use UFF, same thing. No idea what that reference point is because I just don't do the UFF or CHARM or IAMBR. And so this was a little stressful for me doing this calculation because I wanted to get the same delta H for my ammonia, and it did work out. But as I was doing the calculation, I was like, oh. Now it's been a while since I don't exactly remember what the model chemistry was. So shame on me for not telling you this is B30IP, a 6-31G. It probably is, but I don't know. I have to go back and do the calculation. Should have wrote it on here, and that's a problem for my notes. But you see they calculate independently the hydrogen atom and the nitrogen atom. And I take the energy of the hydrogen atom here, and I multiply by 3. And I take the energy of the nitrogen and add that to it, and I get the negative 113 Hartrees for the 3 hydrogen and 1 nitrogen atoms. And so converting that to kilojoules per mole, and really we're just dealing with sort of one reaction here, so the per mole cancels. So this is the one that you would want to use. Look at that number. Okay. And so I kind of throw out that it's 25 kilojoules per mole per Hartree. But you want to be more precise than that because Gaussian's giving you 7 digits of information. And you don't want to throw away the last 4 or the last 3, right? So go ahead and use that full conversion. This had to use like Avogadro's number out to 7 decimal places or 6 decimal places, and this used the definition of the joules of a Hartree out to 7 or 8 decimal places. So that's your number to use right there to convert Hartrees to kilojoules per mole. And so then this is the ammonia calculation. You put that into Gaussian, calculate it, you get negative 113.0188031 Hartree. And you see it's only different in the 4th decimal. Let's see, no, it's different in the 2nd decimal place. Okay. But those are significant differences. So when you see those, if you just wrote minus 113 and then you do calculation on ammonia, minus 113, you're like, there's no difference. So yeah, the decimal places are really important. So I almost never type them in. I always copy them. So I find them in the log file and I copy and paste. Because if you're typing, you're going to swap 2 numbers, and that could be huge. Yeah. So these reference state for enthalpies of formation is a pure element in its most stable state at 298 in 1 bar. So for oxygen, that's O2, etc. Same thing for Gibbs energy. Different reference state for Gaussian than for this. But you're familiar with these tables, these thermodynamic tables, and the things to pay attention to, notice where the zeros are. So this is nitrogen atom at the top. That's a pure element, but we don't have nitrogen atom running around at 1 atmosphere in room temperature. We have N2. So look where the zeros are. N2, the zeros by N2 tell you that's the standard state at 1 atmosphere. So you could actually use these tables to kind of judge which form of an element is the standard form at 1 atmosphere in room temperature. The oxygen down here, O2, I mean, you had a choice between O2 and O3. Let's say you didn't know. Okay? Right? And so you look at this and say, yeah, okay, it's O2. Yeah. Which is an element that you might need to use this table to decide which is the most stable. Sulfur may be a good one. Yeah, S8. Okay, so you have lots of options for sulfur. S8 would be the standard element form. But the one I'm thinking of is carbon. Right? Diamond or graphite? Do you know? It's graphite, yeah. Diamond's not much, but different, but it's different. It's a little above graphite. So it seems strange, but graphite's more stable than diamond. So I think, that's a better option for an engagement ring. It's more stable. No, I get some no's. But honey, it's more stable than diamond. Your diamond is going to decay over time, potentially. One day, maybe. I don't know. There might be an activation energy, So, yeah, and then another thing to point out is you got to really pay attention what form the substance is in. If it's not a pure element, like water, one of the most common mistakes is deciding whether you're dealing with liquid water or gaseous water. So you might see a combustion reaction. You want to calculate the exothermicity or the enthalpy from that combustion reaction, and you don't have the states written in the reaction. So which one do you use? So if you use liquid water, you get the higher enthalpy exothermic than if you use gaseous water. So because you get the heat of vaporization out when you let it go to a liquid. But in an automobile or some kind of situation where you're using combustion, are you going to capture that vaporization energy in the cylinder? Think about the temperatures involved and the speed involved. So you burn your fuel with oxygen, you produce CO2 and water, it pushes on the cylinder because it's a hot gas now and it's expanding, and it leaves. Does that water leave as a liquid or as a gas? Yeah, so you would want to use the one that's giving you the lower delta H. This is called the lower heating value. It's just something to think about. You got to make a decision whether you're going to use liquid water or gaseous water in these thermodynamic calculations. And you've got to think about the situation, the application. If you're wondering about the heat generated in your tailpipe and everything like that, you're probably going to get condensation of water in your tailpipe. So you're going to capture the rest of that energy. It's going to heat up things in your car. But in terms of the energy you're going to get out of it, you're going to only get the lower of the two heating values. The upper heating value includes the condensation of water. The lower heating value does not. It sounds weird, but because water is lower in energy than steam, but we're talking about how much energy you get out of the reaction, how exothermic it is, and the lower number is using gaseous water. Yeah.
I'm curious, do you know why hydroxide ion is negative for the partition?
Yes. Okay. So the entropies are strange. You know, we talked about this, sort of quantum mechanical energy. You look at the partition function as it goes down and temperature goes down, entropy is dropping, and so on. But these S's are defined as sort of the zero entropy is at absolute zero for a perfect crystalline atomic substance. Okay, something like helium, cooled down to absolute zero. Even then, though, helium is going to have vibrational modes that we can't quench out. Okay, so it's likely to have some residual entropy, but that's our thermodynamic definition of entropy. But when you have an aqueous ion like that, it's not like a pure substance. It's surrounded by a solvent cage. And so water had more entropy without that ion than it has with the ion. And so really this S for ionic substances in water is really a delta S, because it's hydroxide in water and it's compared to water without the hydroxide ion and water with the hydroxide ion. So you put an ion in water and it creates order. It's creating order in the water system, so those water molecules are attached, and essentially you've reduced the number of free water molecules in the system, so it's a negative entropy.
It's like linear, so if you reduce the amount of place where water could
yeah, it's going to disrupt some of the hydrogen bonding in water, but it's going to provide structure to water because of the negative ion. The hydrogens are going to be pointing to the hydroxide, and so that's now ordered, so it's a lowering of entropy.
And why wouldn't we see the same thing with like ammonia?
It just depends on the strength of what's happening in water, so that ionic effect is stronger than just the hydrogen bonding effect of ammonia. Yeah, and so you should see, are there any other cations or anions? Some of the cations, there's ammonium.
Yeah, that's what I was thinking.
Yeah, and it just doesn't have a big enough effect, or as big effect as a hydroxide. But like a aluminum 3+, really locks in the water. In fact, it locks it in so much that sometimes it will steal a hydroxide and pop off a proton and become acidic. And so then we can do this calculation. Let's go ahead and do this one by hand. This will be fun. It's 9:44. Yeah. So this should be pretty quick. So we have, let's calculate delta G in formation. So we have in O here, that's our That's our product. And so we have 86.7 positive. And we subtract our reactants, minus 230.1, and then that was oxygen, and the nitrogen's up here, minus 455.5. Okay. And so add these together. Someone please.
Negative 600-ish.
Okay, let's go with that. So negative 600, because that'll be close enough for our purposes. And this is kilojoules. So by multiplying by the number of moles, we had 1 mole of NO, we had 1 mole of nitrogen, 1 mole of oxygen. So the per moles are gone. So this, for this reaction, as it's written, it's minus 600 kilojoules, estimated to one significant figure. Okay, so that's delta G of reaction. It really should be reaction. Now K is equal to minus delta G over RT. E to the minus, yeah. Okay. So let's calculate that. Minus 600 kilojoules over 0.00831 kilojoules per mole Kelvin. And let's do this at 298 or 300. We can do 300 Kelvin.
Now I have a question in what you wrote.
Okay.
So it says e to the negative delta g. So on the second.
Oh yeah. So then it's the thank you. Very good. It's a negative inside there, so it becomes positive, right? Yeah. So we end up with a hugely positive E. So someone please do this math for me.
2,000 over 8.
You know, earlier we did 300 times 0.008, and it was about 2.5, right? So yeah, it was. So this base, the denominator was about 2.5, or let's say 3. So 600 divided by 3, so e to the 200.
I'm thinking like 250-ish.
250?
In my head.
Okay. So we'll do that, 250. So e to the 250. Which is a lot bigger than 1.
Yeah.
Okay? I want to write this in terms of exponential or scientific notation. We've got 1 minute, okay? So put that in your calculator and tell me what it is. Don't bother, it's going to give you an error. Okay? So what do you do in these situations when your calculator gives you an error and you want to think in terms of powers of 10, right? Not powers of E. Just change the base. You can do this algebraically. So when your calculator is giving an error, and I've got these little marks on there, e to the y is equal to some 10 to the x, right? And so you can do that. X is the anti-log of 10 to the x, or log of 10 to the x. And that's equal to the ratio of the natural logs. And so this is your x value. 10 to the x, that x is y over 2.303. So this is equal to, down here, 10 to the 250 over 2.303. So 10 to the 125, right? 120.
Oh, I'm sorry.
Yeah, 10 to the 120. So this is telling you, in terms of powers of 10, how big that K is. And that's a useful little trick. So don't forget your algebra. Everybody's like punching in things in the calculator, and you get stuck because you've got an equilibrium constant that's e to the 250, right? Or 250. And so what are you going to do? Well, just go back to your algebra, change the base, and you can give it in powers of 10, which is a little more satisfying, at least to me. I like to see my equilibrium constants in powers of 10. So I can kind of think, how many zeros is that? As opposed to how many e's is that? Right? So, Next time, we'll talk about how to solve problems, because in this project, you're going to have problems. And so I'll give you a method for how to solve problems. Okay. All right.